All right, hi guys. I'm gonna make a video for our review instead of doing it in class. So hopefully this video helps you. Bear with me as I try to use the marker thing on this. But yeah, let's get started. So again, for this exam on Friday, which is the second, it's only going to be on atomic structure, so it's only unit 4. So when you're going through your guided notes, you should only be looking at the notes that say unit 4 and then all the lessons. It goes from lesson 4.1 to lesson 4.8. Anyways, number 1, the bright line spectrum of sodium is produced when energy is, so again, remember, when we have an atom, right, and we have these electrons, okay, let's say this is just got 5 electrons, so this would be boron. Okay, so right now we have configuration 2, 3, 5 in total, 3 valence electrons. Again, your valence electrons are the ones in the outer shell. Okay, so what we do is this is considered ground state. So this is when the electrons are in their lowest energy state possible. Now we can excite electrons. So if we add energy into this atom, okay, one of the electrons will absorb the energy. Typically it's from one of the last filled shells. So right here, if we're looking at this, we would look at energy level 1 or the first ring. So one of these would go up into here. Okay, so now we would have this electron in here. It would no longer be 2, 3. It would be 1, 4, and we would be in the excited state. Now, again, in order to go from the first energy level to the second energy level, this electron right here had to absorb energy. Now, the way that you get the bright line spectrum, which is, remember that graph with all of the lines at different wavelengths of light, is eventually this electron is not going to hold onto all of that energy. Eventually, it is going to come back down. Okay. And what does it do with that energy? It has to release the energy. So energy is released. Again, here it is. Bear with me while I try to write. So energy is released. Now, when the energy is released, okay, it comes back down to the ground state. So it returns to a lower level. So let's look at our options now. So we know that the bright line spectrum only occurs when the electron comes back down. So we have to go to a lower shell, and it does this by releasing energy. So it's definitely not this or this, okay? We don't absorb energy to get to a lower level. We release energy to come back down to our original energy levels. So it's between really 3 and 4. See, 3 releases energy as electrons move from higher to lower electron shells. Yes, okay. Again, we went from this one up here, the second energy level, back down to the first energy level. So this one wouldn't make sense. Okay, moving on. Let me try to erase this. I don't really know how to do that. There we go. Okay. All right. Now, second one. The valence electrons of a germanium atom in the ground state are located in which one of these shells? So what we need to do is go to the periodic table. Here's our lovely periodic table. And they're talking about germanium. Now you can do 2 things. You can look at germanium, look at its electron configuration. Okay, so it's 2, 8, 18, 4. Or what you can do is you can look at what period it is in. So these are the periods on the sides. Again, those are the rows going across. You can see that germanium is in the 4th row. That means that it has 4 shells. So you could do either of those. You can look at the configuration, or you can just look at the period that it is in. Remember that the valence electrons are in the outermost shell, and the outermost shell of a germanium atom is the 4th shell. So this one would be 4th shell. Okay. Again, let's move on. Okay. A sample of matter, let me get my pen. A sample of matter must be copper if each atom in the sample has 29 protons. Again, 29 protons. This is describing your atomic number. All right. Next one. Atoms in the sample react with oxygen. This is explaining a chemical property. 3, the sample melts at 1768 Kelvin. Melting is a physical property. 4, the sample can conduct electricity. Conducting heat or electricity is also a physical property. Now, many different things can conduct electricity. There could possibly be some other substance that melts at 1768 K. A lot of things react with oxygen. Again, the thing that would define an element, as we have been talking about, is the number of protons that it has, or the atomic number. So this one is simply choice 1. All right. Next one, what is the number of protons in an atom with the electron configuration 2, 5? This is talking about element 7. Okay, it's got 7 electrons. If it's got 7 electrons, it's also going to have 7 protons. So those things should be equal in a neutral atom. And by the way, they're talking about nitrogen. Nitrogen is number 7. So protons and electrons, again, should be equal in a neutral atom. All right, let's move down. Oh, gotta erase that. All right. Next one. What is the net charge of an ion that has 8 protons, 9 neutrons, and 10 electrons? Now, they're asking for a total charge. This 9 neutrons is extra information. We don't need it. Why don't we need it? Neutrons don't have any charge, so they don't contribute to the overall net charge. But we have to think about the electrons and the protons. So we've got 8 protons. Each proton has a +1 charge. So that means that from all 8 protons, we get a +8 charge. We've got 10 electrons. Each one has a -1 charge. So if we've got 10 of them, that's -10 total. Now they want the net charge. Net is all of it all together. So 8 plus -10, that is -2. So to be specific, this is an ion that is negative. We call that an anion. Remember, anion, like onions, makes you cry. That's bad. Okay, so this one would be choice 4. Okie dokes. Next one, let me erase this before I move on. Okay. Compared to the atoms of nonmetals in period 3, the atoms of metals in period 3 have, well, okay, if we're in a period, first off, those are the things that are going across, like this. Period 4, period 5, period 2, whatever. Okay. Now, again, if you were in the same period, all of the elements there have the same number of shells. So if you look, for example, in period 2, right? Lithium, beryllium, boron, carbon, so on and so forth, all their configurations only have 2 energy levels or 2 rings. So 2 of these choices just absolutely don't make any sense. And that would be 3 and 4. If they're in the same period, they have the same numbers of shells. Now, let's look at the valence electrons. So again, we're in period 3, and we're comparing the nonmetals and the metals. Now we can see here, if we're in period 3, these are the metals right here: sodium, magnesium, and aluminum. Those are the 3 metals. Silicon is a metalloid, and phosphorus, sulfur, chlorine, argon, those are all the nonmetals. So you can see here, sodium has 1 valence electron. Again, the valence electron is the one in the outer shell. Magnesium has 2, aluminum has 3. You can see as you go across that there are more electrons in each element as you keep going. So let's go back to the question. Again, compared to the atoms of nonmetals in period 3, the atoms of metals they should have fewer. Okay, again, sodium only had 1, magnesium had 2, carbon had 4, or whatever it was. Let's see, go back, not carbon, sorry. Silicon had 4, phosphorus has 5, sulfur 6, so on and so forth. So in comparison, the metals, they have fewer valence electrons, choice 1. Alrighty, let's go back up to the top of this page. I feel like I might have marked that wrong on the actual review. But anyways, it should be fewer valence electrons, yeah. Okay. Anyways, okay. In the electron cloud model of the atom, by the way, that is the most current one, right? That's the one with all of the dots. An orbital is defined as the most probable. This is literally just definition, guys. This is just the most probable location of an electron, okay? So really, this is just something to commit to memory. Again, the electron cloud model is like this. It's got the nucleus in the center, and then it's got all these dots all around it. The more dense they are, means that you're more likely to find electrons there. Again, as you move further away from the nucleus, the dots become more sparse or less dense, meaning that you're less likely to find electrons out there. Okay, and again, orbital is basically a shape, a 3D shape around the nucleus in which an electron can be found. That is all. Sometimes the shape can be a circle. Sometimes it can look like this, or it can look like a bunch of different things. But yeah, again, it's just a shape, it's a space around the nucleus where you are likely to find an electron. Okie dokes. Moving down. Which statement compares the masses of two subatomic particles? Number 1, the mass of an electron is greater than the mass of a proton. What would be easier right now would just to write out the masses of everything. So we've got neutrons and protons. Those are both in the nucleus, and they make the most of the mass of the atom. They have the same mass. They are both 1 AMU, or you can also see it written as 1 U. Electrons, for all intents and purposes, has basically no mass. So we just say that it's 0, pretty much. Okay. All right. So let's go back to number 1. The mass of an electron is greater than the mass of a proton. Clearly, we can see that electrons have no mass, so no. The mass of an electron is greater than the mass of a neutron. Also no. Number 3, the mass of a proton is greater than the mass of an electron. Yes, that works, okay? Proton has 1 AMU for mass, and electron has nothing. So this one makes sense. Let's just look at number 4 anyways. The mass of a proton is greater than the mass of the neutron. That is not true. You can clearly see that they are equal. They are both 1 AMU or 1 U. Okay, moving on. All right, which statement matches a subatomic particle with its charge? Number 1, a neutron has negative charge. That is not true. Neutrons have 0 charge. A proton has a negative charge. No, it's got a positive charge. Again, positive proton. P starts with P. They both start with P. Okay. 3, a neutron has no charge. Yes, that is very good. Okay. Again, neutrons are neutral. And now that we're in our nuclear unit, we can show it like this. So neutron has mass of 1, charge of nothing. And let's just look at the last one. Proton has no charge. That is not true. Again, we know that protons are positive. So that one should be choice 3. All right. Which phrase describes 2 atoms that contain the same number of protons, but a different number of neutrons? Again, this is just a definition, okay? So when you have 2 atoms or multiple atoms that have the same numbers of protons, okay, that means that they're the same element, but their neutrons can differ. And this is an isotope. Again, these are basically the versions of elements. Examples could be carbon 12, carbon 13, carbon 14, so on and so forth. This seems a lot more familiar to us now because we have started nuclear chemistry. All right, so that one is choice 2. Again, simply just a definition sort of question. All right, next one, last one for this page. What is the total number of neutrons in an atom of oxygen 18? So I'm going to rewrite this. Actually, first, before I do that, I'm going to go here. If you don't remember, that's fine. You have the periodic table at your disposal. So oxygen, no matter what type of isotope it is always going to have 8 protons. So let me go back and we can rewrite this. So this version of oxygen has a mass of 18, but again, its atomic number is always going to be the same. It's always going to be 8. Now they're asking specifically for the neutrons. How do we get neutrons? You always take the mass number, which is up here, and you subtract your atomic number. So it's simply 18 minus 8, and that is 10 neutrons. So our answer for this is 10. Okay. In case we also want to know how do we get the number of protons, it is simply this number, the atomic number. The atomic number, if it's a neutral atom, can also tell you the number of electrons. So if this was a neutral atom, we would have 8 protons, 8 electrons, and 10 neutrons. So choice 3. Okay, next page. All right, naturally occurring isotopes of bromine. So again, these are the isotopes. These are the versions of each element that exists. All of the elements have isotopes. They have different versions of themselves. And these versions differ in their neutrons, meaning that their masses are going to be different. Now, again, for example, if we look at bromine, not all bromine is bromine 79. Some of it is also bromine 81. So it's about half and half, pretty much. Okay, but for this, we can't just simply take a regular average. We have to do the weighted average. So what we really have to do is we have to multiply these two numbers. You do your atomic mass times your natural abundance. Do it again here, atomic mass times your natural abundance. The only problem here is that you can't multiply it by a percent. So this decimal needs to be moved over 1, 2 spaces right over here. Same for this one, 1, 2. Then at the end, you would add these all up. So these things get added. So let's look over here. First of all, I know that I can eliminate choice 1 and choice 2. I can see that the abundances right here and right here have not been converted to decimal form. So these are out. Next one, we want to make sure that everything matches up. I can see 78.92U times 0.5069. So this one matches so far. Then we have 80.92. That's the atomic mass for bromine 81, multiplied by its abundance, which is also turned into decimal form. So this is the one that makes sense. Okay. This one doesn't make sense because they basically switched up. They swapped the atomic masses and the natural abundances. So this is just wrong. Again, you should be multiplying across. All right. Next one. All atoms of an element have the same, again, this is just a definition, and we've said this one so many times. They have to have the same number of protons. Again, they also have to have the same atomic number. That's what your protons is, your atomic number. All right. Next, which electron configuration represents the electrons of an atom in an excited state? So again, what we want to do is take a look at our configurations that they're giving us. The first one I can see is 2, 7, 3. Right off the bat, I know that this is the correct one, okay? The second shell can hold 8 in total, but it's not filled. But then I have another shell here. So really what we did was we took one from the second shell and we excited it into the next shell, the third shell. So this would be our option. All right. Moving on. Next one. What is the approximate mass? This is a good question. What is the approximate mass of an atom that has 10 electrons, 10 protons, and 9 neutrons? Again, this is a similar to another question where they give you information that you don't need. Kind of trips you up, tricks you. Which of these don't have any mass? It's the electrons. So when we get the mass of the atom, we don't care about the electrons. They basically have a mass of 0. All we care is about the protons and neutrons. They both have the same mass of 1 AMU. So if you have 10 protons and 9 neutrons, you've got 19 things that all weigh 1 AMU. So the total mass is just 19. That's it. 19U or AMU, whichever one. 19 in total. Again, avoid the electrons if they're asking about mass. All right. I think we've got a few more questions. Okay, 2 more. All right, here's our bright line spectra. So again, all you got to do is just match up your lines, but make sure that all of your spectral lines match to the mixture. So we've got this mixture of 2 different elements, element A, Q, E, G. These are just symbolizing elements. Those are not actual symbols for real elements. So I can see here, I've got this spectral line close to 400 nanometers, and I can see that it lines up very well with this first line in element Q. I can also see that this second spectral line in Q also matches up right here. So I know that I've got Q, but I should make sure, just to make sure that these other spectral lines are also there. So I've got this line right here, and it matches up perfectly. This one here matches up as well. So I know I've definitely got Q in the mix. So it's automatically not 2 and it's not 4. And so it's between 1 and 3. Now I can see that there is this whole bunch of spectral lines over here, and I can see that there is a whole bunch of spectral lines over here. So pretty much off the bat, I can just tell that it is A by looking at it. Again, these 2 spectral lines right here match up here. These 4 are clumped together right around 450 nanometers, so on and so forth. You can go ahead and check all of the other spectral lines, but it does match up. So this should be A and Q in our mixture. All right. scroll down. Last question. So, gotta move my stuff. I know y'all can't see it on your side, but I got stuff all over the place. No? Okay. All right. So we've got another question like this, except we have to set it up ourselves. Okay. Again, bear with me because I have to write a lot for this. So we've got copper, two naturally occurring isotopes, copper 63 and copper 65. Again, they vary in their numbers of neutrons. If they vary in their number of neutrons, then they obviously also vary in their masses. So in order to get the mass of copper that you see on the periodic table, you have to take the weighted average. So again, what we're going to do is we're going to multiply our atomic mass by our natural abundances. However, before we do this, we have to move our decimals for our percentages over 2 times. So these are going to get multiplied, these are going to get multiplied, and at the end, it's all going to get added up. So what we've got, first step, is 62.93. That's our mass for copper 63. Multiply it by its abundance. However, your abundance has to be changed into decimal. So 0.6917. And then this is going to be added to these two things multiplied. So for copper 65, the mass 64.93 times its natural abundance. Again, make sure that you change that percentage into a decimal. So 0.3, that does not look like a 3, but pretend that it does. 0.3083. And this is it. I don't have to solve for it. It says showing numerical setup. So try to be really careful, pay attention when it says showing numerical setup versus actually calculate or determine. This does not say calculate the atomic mass, and it doesn't say determine. It just says show a numerical setup in order to calculate, but you don't have to actually calculate. So this is the final answer, and you can just leave it at that. All right. So I hope this was helpful. Bear with me as I try to figure out how to end this. All right. Anyways, I hope this was useful. You can play it back as many times as you want. And good luck, guys. Good luck studying. Also, I posted a bunch of other videos, one for pretty much each lesson that we have. Just please note that I didn't go over Lewis dot structures in this review. So that might be something that you want to review through a video or through your notes. Anyways, guys, good luck.